The Q represents the free electrons. When these electrons manage to move, the motion or the movement of the electrons creates the current, electric current. But the electrons or the charges in a conductor will not move until something is done. And what is that? They will only move when a source of EMF is connected to drive them. So when we connect a battery, example, battery generator or dynamo, the battery generator or dynamo creates the potential difference. Once there is a potential difference, current flows, or the charges would flow. When the source of EMF comes in, a force is exerted on the charges or the electrons. So we have a force acting on the charges or the electrons. This force is what pushes them. And this is because Newton said whenever there is an external force acting on a body, there is acceleration of the body. The body's speed increases or decreases. So the body accelerates. So the source of EMF is what is responsible for the acceleration of the charges. Once the charges move, we have current. Now, what happens is that because there is an external force, we have external force, which we refer to as electric field. Electric field, because they have intensity. The electric field, hold on a second, I'm coming. My board nearly dropped. I'm coming in. Let me fix it and get back to you. All right, so back from commercial break. So the electric field exerts a force on the charges. Isra, you listening? And Mary?
Yes, please.
The electric field exerts a force on the charges, right? So imagine yourself being the charges. When there is something which is pushing you, you would begin to accelerate. Now, when that external field, which accelerates the charges, comes in, it also increases the kinetic energy of the charges. So the electric field, which is the electric force, electric field increases the kinetic energy of the charges. Please take note of the charges. Here the charges are free electrons. So electrons. Now from atomic theory or kinetic theory of matter, average kinetic energy of particles is directly proportional to the absolute temperature. Meaning that as the field causes the kinetic energy of the electrons and then the charges to increase, the temperature of the whole conductor also increases. Okay, now the conductor is made up of atoms atoms, individual atoms, a lot of atoms. Around each atom, we have the free electrons in the valence shell. So, assuming we are talking about single free electrons for each atom. For current to happen, we expect these charges to move. And when they move, we have current flow, electric current. And the force, electric force is what does that. But because the temperature of the conductor is increased so much, the atoms vibrate at their mean position. While the atoms vibrate, there is a greater tendency that they will kick off free-flowing electrons. And so when free-flowing electrons are kicked from their path, okay, that is what causes resistance. If we are supposed to have 10 charges flowing in a particular direction, then it means we have 10 number of charges within maybe 1 second. But when it happens that as a result of the vibration of these atoms, some of the charges are not off and they don't get to their destination, it means we have reduced the number of charges flow. And the moment something causes the charges flow to reduce, we have lesser conductivity, and that is resistance. So resistance in a circuit is as a result of vibration of the atoms of the conductor or the material, which knocks or reduces the number of free charges or electrons that must flow within a given time. Please, Mary, Insha, and Kay, are you okay?
Please, can you repeat that?
So resistance is caused by the vibration of the atoms of the material. The material is a conductor. Now, as the atoms vibrate because of the external field introduced within the conductor, they will vibrate. And as they vibrate, they knock off some free-flowing electrons that must flow in a certain direction to give us current, electric current. So when the atoms vibrate so much, resistance increases. And how will the atoms vibrate? The atoms will vibrate so much when the temperature of the conductor increases. Mary, are you okay? Safo? Okay.
Yes.
Are you? So, in a conductor, when temperature increases, resistance also increases. In a conductor, when temperature increases, resistance also increases. So in a metallic, let me write something down for you. In a metallic conductor, let me change this marker. It's not so difficult, but in fact, if you are not careful, you won't understand. So in a metallic conductor, when temperature increases, I think I must change this marker. In a metallic conductor, when temperature increases, resistance also increases. Therefore, reducing or decreasing conductivity. So when temperature resistance increases, it reduces conductivity. Okay. So when you increase temperature, you are increasing resistance. And what is the reason for which when temperature increases, resistance also increases? What's the reason? Yes. Can somebody tell me what is the reason behind an increment in resistance as a result of increase in temperature? Can somebody tell me, K, Mary, and then Inshira, why is it that when temperature increases, resistance also increases? Why? Can somebody try?
I'll say it's because the increase in temperature allows the molecules the atoms of the conductor to vibrate. The temperature gives the atoms energy to vibrate. And as they
Thank
vibrate,
you.
they will knock off the electrons.
Thank you. So the whole thing is that I just told you that increase in temperature, average kinetic energy, KE, is directly proportional to absolute temperature. Or absolute temperature is directly proportional to average kinetic energy of particles. So the moment you increase temperature, the average kinetic energy of the atoms would also increase. When the average kinetic energy of atoms increases, okay, the atoms will vibrate so much and then kick out free flowing electrons. Mary and Ishra, you fine?
Yes, please.
When atoms vibrate so much, they would kick off free flowing electrons. So the number of free flowing electrons would reduce as a result of the vibration of atoms.
So the electrons are vibrating very rapidly.
The atoms.
The atoms, okay.
The atoms of the material are vibrating as a result of increase in temperature. It is the electrons that must flow, but electrons are around the atoms. So when the atoms vibrate, they would displace electrons that are moving. Okay. So that is the reason. And that also explains the reason why in Ohm's law says that V is directly proportional to I at constant temperature. If you don't keep the temperature of the conductor constant, the current flow would not be uniform or steady. It will be changing. All right.
Okay.
Okay. So, Mary, do you have any question? So factors that affect resistance of a metallic conductor. We have one temperature. Temperature affects the resistance of a metallic conductor. The greater the temperature, the greater the what? Yes, the greater the temperature, the greater the what?
Resistance.
Resistance. 2. What do you think is another factor responsible? Okay, do you have any to this share with us factors that affect the resistance of a metallic conductor?
I'll say the length of the metal conductor.
The length. Good. So the greater the length, the greater will be the resistance. So length of the conductor. Then we also talked of cross-sectional area. Cross-sectional area A. And then the nature of the material. The nature of the material used as a conductor. The nature of material used as a conductor. And the nature of the material is what we said to be resistivity. Because different materials offer different opposition to the flow of current. So if you use aluminum, you get different resistance. If you use copper, you equally have a different resistance, and so on and so forth. Different materials offer different opposition. So when you put these together, we have resistance R directly proportional to the length, resistance R inversely proportional to the cross-sectional area, okay? And when we put them together, we have R directly proportional to L over A. R is equal to a constant of proportionality, L over A. This constant of proportionality, K, is the specific resistance offered by the conductor, which we call as resistivity. So R, therefore, is equal to rho L over A. R is equal to rho L over A. So these are the factors. Temperature isn't a physical one. It is not physical. The reason for which we don't introduce temperature into this. We are looking at the physical factors that affect the resistance of a metallic conductor. Please, with the cross-sectional area, a wire has the area of a circle. So the area of a metallic conductor is the area of a circle. The area of a metallic conductor is the area of a circle. So pi r squared is the cross-sectional area. Please, any question?
So yeah, so the rho stands for density.
The rho stands for resistivity.
Resistivity. Okay.
Resistivity. So where let's define the variables. Where rho is equal to resistivity. And resistivity is the specific resistance to the flow of current. Then L is the length of the conductor. Then A is the cross-sectional area. R is resistance. Please, if R is equal to rho L over A, let's make rho the subject. Let's make rho the subject of the equation. Make rho the subject. And we want to determine the SI unit of resistivity. Mary, when you made rho the subject, what did you say?
Mr. Eja, please, I got RA all on L.
So R A all on L. So what do you think is the SI unit of resistivity? What do you think is the SI unit of resistivity? Mary, Isha, what's the SI unit of resistivity?
Please, I said that it is meter.
Yes, it's ohm meter.
Oh, okay.
Ohm meter. Now the inverse of resistivity. 1 over rho is what we call as conductivity. Okay, sigma. So sigma, which we call as conductivity, is equal to the inverse of 1 over resistivity. So sigma, which is conductivity, is 1 over rho. What then is the SI unit of conductivity? K. What is the SI unit of conductivity? Okay, what's the SI unit of conductivity? Okay, it's not here. Okay, Mary.
I'll say meter.
Okay, if you are ready, go ahead.
I'll say meter ohm.
Meter ohm, no. No. Mary, what do you also think?
The inverse of ohm meter.
So per ohm per meter. Per ohm per ohm per meter. Because it's 1 over the whole of this. So per ohm per meter. Is that okay? Then the inverse of resistance. The inverse of resistance is known as conductance. Conductance is equal to 1 over R. So please note the difference. We have conductivity, which is the inverse of resistivity. Okay. Then we have conductance, which is the inverse of resistance. So 1 over resistance. And so conductance is equal to 1 over R. Therefore, SI unit of resistance is per conductance is per ohm. Per ohm. I want us to just go through the theory, then we apply this in solving questions. Let's look at when you have a number of cells connected in series and in parallel. We have a number of cells connected in series and then in parallel. Or before that, okay, before we look at number of cells connected in series. Let's look at resistors connected in series and in parallel. Then we apply that to our cells. Because the cells one would apply resistors. So resistors connected in series and in parallel. Inverse of resistivity is equal to conductivity. So conductivity sigma is equal to 1 over rho. Then the inverse of conductance is equal to resistance. Inverse of conductance, resistance is equal to conductance. So please note the difference. So resistors connected in series and in parallel. Resistors connected in series and in parallel. After that, we'll also look at a combination of these two. So when two resistors are connected in series, it's similar to when a number of you are made to stand, okay, in a horizontal manner. I'm here, one is here, on, followed by the next, on and on and on. And then we hold our hands. So I hold your hand, you also hold the hand of another, on and on and on. This is series connection of resistance. So resistance in a circuit is represented by please play back. Hello. Hello.
Hello,
Hey,
Mr. Ejia.
hey, Rachel, you are welcome. Okay, so resistance in a circuit is represented as this. So this is a resistor, or so these two symbols are what we represent as resistor in a circuit with capital R on top. So if you want to connect two resistors in series, either you use this symbol, the first one, or the second one. So two resistors connected in series, it's like standing next to the other. Okay, resistors are not like cells where there are polarity, positive and negative. No. So this is a resistor. What you see here are wires. So another resistor connected to one other resistor will be this. So these are two resistors connected in series. R1 and R2. 1 and 2 to denote that they are different resistors. In fact, we said a resistor is a device. Resistance is the opposition to the flow of current, or the magnitude of the opposition to the flow of current. But a resistor is a device that opposes the flow of current. Resistance is the measure of the opposition to the flow of current. By a resistor, the measure of the opposition offered to the flow of current is resistance. When we talk about resistor, it is a device that offers or opposes the flow of current. Please, are you okay? Hello, are you okay? Are you people there or you are gone?
Please,
We are
we're
here.
here.
Are you okay with the explanation?
Yes, please.
So when we, please pay attention. Online teaching is not easy, so pay attention. I beg you. I'm coming. So when we talk of resistance, a measure of the opposition to the flow of current, a resistor is a device. So if I indicate R1, this is the magnitude of the resistance offered by this. R2, this is the magnitude of the resistance offered by the second one. And this is two resistors connected in series. Two resistors connected in series. If I have to show that for three resistors connected in series, all that I do is to join another one. So these are three resistors connected in series, R3. Another way of doing the same thing is this. So this is R1, R2, R3. Now for parallel connection of resistors, this is similar to Inshira is here. Mary stands behind Inshira. So this is Inshira and Mary. Now what I want to do is that I want Mary to touch the shoulders of Inshira. So the left hand is stretched to establish contact with the left hand of, or the shoulder of Inshira, just as you do during assembly, school assembly. So this is two people, okay, connected in parallel. So if I'm establishing or indicating two resistors connected in parallel, one is here, the other is just at the back of. So a wire from one end, the right hand, establishes contact with the right hand of the first one. And then a wire from the left hand of the other one, establishes contact with the left hand of the. So these are two resistors connected in parallel. Please, are we okay?
Yes,
Yes, please.
If it's about three resistors, the same thing. You just include another one. Another one connected as such. All right. So let's look at what goes into resistors. What happens when resistors are connected in series and in parallel? Please, if you have any question, ask. If you have any clarification to what we've said so far, please ask. So two resistors connected in series. That the resistors must always be connected for current to flow. We must always connect them to a source of EMF. So let's connect this to a source of EMF, a battery. So conventional current flows from the positive terminal to the negative. So I would always flow from positive to negative and then enter into, yes, from positive to negative. When resistors are connected in series, the key features, so features of series connection, of resistors. One, when resistors are connected in series, and then can you share with me, in fact, you've been reading, so can you share with me some of the features of resistors connected in series? When we connect resistors in series, what are the keynotes or features? Yes. Rachel, Mary, Inshira, and Kay. What are the features of series connection? Rachel starts. Hello, Rachel. Oh, she's not here. Mary. Mary.
Mr. Yes, Mr. Ja. Mr. Ja, please. Mr. Ja.
Mary, I'm listening. When
Please,
resistors
I
are. Go ahead.
Please, I think when the resistors are connected in series, they confer a greater resistance because the total resistance is equal to the individual resistance.
Okay, that is Mary's view. Ishra, what do you also have to say? When resistors are connected in series, what happens?
Um, um,
If you have no
they have
idea, let me know. Okay, do you have
they
any
have the,
idea?
I don't know if it's correct.
Try.
I said they have different voltages, potential difference or something. The V.
Okay. Okay, do you have any idea?
So
All
the
right.
same thing can flow through.
The same what?
The same amount of current flows through each resistor. The total current in the circuit is the same for.
Okay. All right. So, yes, one of it is what has been said by Key. When resistors are connected in series, now, same amount of current flows through the circuit. Same amount of current flows through the circuit. So the current that comes into R1 is the same as the current that comes into R2. What is the reason why? You see, current is the rate of flow of charges. The same conductor wires, meaning this source just pushes the charges that are free. Their freeness simply means that they are not attached to the nucleus. So this is what is exerting a force on them, on the charges. Once the conductor is the same, the charges will not be different. And this is being pushed by the source. So the same current will come to this, it will come to this on and on and on. Now, when it comes to our homes, and R1, R2 represents maybe the spending or current usage in different houses. Maybe what I have in my home is different from what Rachel has, what Kay has, what Mary has. And that is what we have indicated by R1, R2, R3, meaning R1 is different from resistance of R1, different from R2. So when it comes to this point, the rate at which the household uses the current will be different. So R1 will be different from R2, R3, on and on. And that difference is what we call as potential difference. So when I pick any 2 points over here and determine the potential difference across R1, V1, because R1 is different from R2, V1 would also be different. So different potential drops or voltage drops across the resistors. So V2, V3, on and on. But the same current flows through the resistor. So for series connection, same amount of current flows flows through the circuit. Flows through the circuit. But different potential difference or voltage drop. Potential difference or voltage drop across the resistors. Because the resistors are different, the voltage drop would also be different. Okay, meaning that if the resistors have the same resistance, there will be the same voltage drop. Please, are we okay here? Are we okay? So these are the features of resistors connected in series. Now, let's look at total resistance. So, for R1, Isha, are you there? Mary, are you there?
Yes, please.
Yes,
For
please.
R1, the voltage drop across resistor 1 from Ohm's law, V is equal to IR. Therefore, V1 will be equal to same current flows through them. So VI times R1. Then R2 would also be equal to V2 is equal to I times R2. Now the voltage drop across this, across R1, voltage drop across R2. When I sum all of them, it must be equal to the source EMF or the source voltage, V. So we are denoting the source voltage by V. So V, therefore, is equal to V1 plus V2. Let's then substitute V1 and V2. So IR1 plus IR2. Let's factorize I out because it's common to each of the terms. So I out, we have R1 plus R2. When you divide through by I, we have V on I equal to R1 plus R2. From Ohm's law, what is V on I? What is V on I from Ohm's law? Yes, I need a response. Pardon?
R.
Good. So it means since V on I is equal to R, this R is equal to the total resistance, R1 plus R2. So when resistors are connected in series, the total resistance is equal to the summation of all the resistances within the circuit. Okay, so you must be familiar with this. The features. You must be familiar with the features and then also be able to derive this. This formula, how to derive the relation for resistance in series total resistance in series, you must learn how to derive them. It's not difficult. Now, supposing R1 is equal to R2, what will be the total resistance? Supposing R1 is equal to R2, what would be the total resistance here? Yes. Mary, it's your question.
Mr. J, please R1.
Pardon?
Please, the answer will be 2R1 or 2R2.
So, what will you say? 2R1, 2R2, what will you say?
Please 2R1.
2R. 2R.
R1.
So 2R. And R represents the resistance of either R1 or R2. They are equal. So the resistance will be, the total resistance will be 2R. Mary, do you understand?
Yes, please.
Okay. All right. So let's then look at resistors. Okay, I want you to do it for 3. Let's have 3 resistors connected in series. So help me derive it for 3. So R3. So help me find the total resistance, RT, for 3 resistors connected in series. I'm giving you 3 minutes. Because there are 3 resistors, 3 minutes. Oh, even 3 minutes is so much. Inshira, give me your answer. 3 resistors connected in series.
I see the total resistance.
Yes.
It's R1 plus R2 plus R3.
Okay, so it's not supposing R1 is equal to R2 and it's also equal to R3. What will be the total resistance here?
To be 3R1 or 3R2 or
Wow.
3R3.
So it's 3R. Okay, 3R.
Okay.
Yes. Okay, are you there?
Yes.
Let's look at resistors connected in parallel. So 2 resistors connected in parallel. Two. So 2 resistors
Okay. Can come and charge it.
Okay, so let's do it for 2. Then you will do it for 3. This is source of EMF V. R1, R2. Now, what are the features of parallel connection? What are the features? Rachel. Rachel, are you there? Okay, Mary, give me one of the features. When resistors are connected in parallel, what are the key features?
Mr. J,
Okay, Rachel can talk now.
Mr. J, my mic is on and off. Right now it has come on. Okay,
And
so I
then
think
do all the talking before it goes off.
for the parallel, the voltage across the circuit is the same.
Isha, come again. Rachel, come again.
So for the parallel, the voltage across the components is the same.
The voltage, you mean the voltage across it is the same? The voltage across the resistors is the same. Okay, so that is true. When resistors or components are connected in parallel, okay, they have the same voltage drop across all of them. So this source voltage is equal to what is here, is equal to what is here. This is because in parallel connection, this is plus, this is minus. A connector is picked from the positive of the source and then linked to this resistor is connected to the positive of the source. This side is also connected to the negative of the source, meaning whatever this side has is what has been given to this. So in effect, this is also would be exposed to a positive potential. This side would also be exposed to a negative potential. Then a wire is picked, connected to this. Already this side has been given to this. Okay, so this is positive, more positive. So this side would also be positive. Wire is connected to this side. This side is also negative. So whatever this has would be given to this side, on and on and on. So in effect, they have all the resistors have the same voltage drop. So if you have 10 of the resistors, they will all, okay, connect to their source in this manner. Please, is that okay? Ishra and Paul, is that okay?
Yes, please.
So all resistors have the same voltage drop across them as the source voltage. Voltage drop or potential difference. So if you have 10 of them connected in parallel, they will all be connected in this manner. Now, current flows from the source, and conventional current flows from positive to negative. For current flow, because when the current gets to this point, there is a junction. In electrical circuit, a junction is a point where 3 or more wires connect. So wherever we have 3 or more wires connecting, it creates a junction. So we have one wire here, another, and another wire. There's a junction. Okay. So when the current gets to the junction, it is divided. some has to go to this side, some has to go to this other side. So we have I1, we have I2. Okay, let us name it to follow R1 and R2. So I2, I1. Okay, but I1 and I2 must be equal to, or must sum up to, the total current coming from the source. So in a parallel connection, all resistors have the same voltage drop or potential difference. So they have the same potential difference, but different current flows through them. 2. So different current flows through them. And them refers to the resistors. Mary, Ishra, and Kay, are you okay?
Yes, please.
So different current flows through them. All right. Let's then derive an expression for the total resistance. From Ohm's law, V is equal to IR. Okay. We've realized that V is equal to V1 is equal to V2. Same voltage drop across all of them. But what varies is the current. So if I'm looking for the current coming into R1, I1 would be equal to V1 over R1. V1 is equal to the source voltage V. So I1 will be equal to V over R1. If I need the current flowing through the resistor 2, I2 must be equal to V2 over R2. V2 is equal to the source voltage, V. So V over R2. The divided current, I1, I2 must sum up to the source current. So I is equal to I1 plus I2. I'm coming. Uncle Jill is calling me from school. I'm coming. All right, so if I is equal to I1 plus I2 and the individual current have been established, then let's put them in. I is equal to V over R1 plus V over R2. Therefore, when we factorize out V, we have 1 over R1 plus 1 over R2. Let's divide through by V. When you divide through by V, what do you have? What is I on V? From Ohm's law, what is I on V? Yes. A question to the class. From Ohm's law, what is I on V?
Teja, please, the inverse of R.
Good. So this is 1 over R. So it means 1 over R is equal to 1 over R1 plus 1 over R2. This R is the total resistance. Now for me, if you have just 2 resistors connected in series. I can find the LCM of this R1, R2. This will be R1 plus R2. So that if I find the reciprocal of this, I have RT to be equal to R1 times R2 over R1 plus R2. And this is the expression for two resistors connected in parallel. Two resistors connected in parallel. So your work is this. Instead of 2, you are given 3. Instead of 2, you have 3. We have R3 here, connected to a source of EMF. How do we obtain the total resistance? Or what is the expression for the total resistance? Start work and think through for me. I'm giving you 3 minutes because we have 3 resistors. Make me proud. So get the expression for the total resistance for the 3 resistors connected in parallel. Rachel, what is your answer?
Mr. Adrian,
What is your answer?
Mr. Adrian, please, RT is equal to R1 plus R2 plus R3 all on R1, R2, R3.
Come again.
Please, I had RT is equal to R1 plus R2 plus R3 all over R1, R2, R3.
I doubt. Look at it again. K. What
The
have you had?
RT is equal to R1, R2, R3, all on R1 plus R2 plus R3.
I doubt. Mary, what's your answer?
Mr. Adrian, please, I had RT is equal to R1 times R2 times R3 all on R2 times RT plus R1 times R3 plus R1 times R2.
I think this is correct. Let's see. So, what is important is to understand that for resistors connected in parallel, voltage drop across all the resistors the same, meaning V is equal to V1 equal to V2 equal to V3. But what varies is the current. So the total current coming from the source will be equal to the current into the first resistor R1 plus I2 plus I3. So all that I need to do is to find I1, I2, I3 and substitute into the equation. Okay. Now, I1 will be equal to V1 over R1. So, but the V1 is equal to the source. So, V over R1 plus I2 would be V2, which is V over R2. I3 will be V over R3. We can factorize out voltage. So we have V when we divide through by V, we have I on V. I on V is equal to 1 over R total or R equivalent. This is 1 over R1 plus 1 on R2 plus 1 on R3. If I want to simplify this, I must take the LCM. And the LCM of this will be R1, R2, R3. Are we there? R1 goes into the LCM 1, remainder R2 and R3. So the remainder times 1. So I have R2 times R3 plus I have R1, R3. I have R1, R2. And this is 1 over RT. So if I want RT, it's the inverse of what I have here. Therefore, RT is equal to R1, R2, R3 over R2 times R3 plus R1 times R3 plus R1 times R2. This is the final results. So whenever you are giving more than 2, I think you must be very careful in handling it. Are we okay?
Yes.
So once for series connection of resistors, this is what we've seen. The total resistance is R1 plus R2 plus ... to the end resistance, meaning the end resistance is the last resistance. Okay, and so we conclude that for series connection, the total or sometimes we describe this as the effective resistance. The total or effective resistance is greater than any individual resistance in the circuit. So practically, if you have an electrical connection and you want the final resistance to be greater, if you have a number of resistance or resistances, and what you so desire, or whoever is designing the circuit, what you want is to have a total resistance which is greater than any one of them. The advice is that connect all the resistors in series. That's a practical application of what we are doing. Connect all of them in series. And when you do that, the final resistance of all will be greater than any individual resistance within the circuit. Please, are we okay?
Yeah.
As we do it, I think we must understand the practical application of it. That's the essence of connecting in series. For parallel connection, we saw that RT, 1 over RT, is equal to 1 over R1 plus 1 over R2 plus 1 over ... 1 over Rn, the end resistance. Okay, now what happens is that when you connect resistors in parallel, the effective or total resistance of all, the effective or total resistance of all the resistors is always less than any one of them. Is less than the resistance of any individual resistance within the circuit, in the circuit. The application of this is that if you have a circuit, a number of resistors, and you want the final or the total resistance within the circuit to be smaller than any individual resistor or resistance within the circuit, the advice is that you must connect them in parallel. And when you connect them in parallel, the total resistance of the combined resistors would always be less than any individual resistance or resistor within the circuit. That's the practical application of connecting in circuit. Okay, there are advantages, there are disadvantages. So I think we've done 345. Let's quickly discuss the advantages and then the disadvantages of some of the series and then parallel connection. And then I think we call it a day. Before then, if you have any question, ask. Now, when resistors or loads can refers to appliances, any device that utilizes or makes use of current. So when you have loads or resistors connected in series, example, if you have bulbs connected in series, that the advantage is that because same current flows through them, they are all given the same level of brightness. So if you have maybe 5 watts bulb, 15 watts bulb, 50 watt bulb, whatever, and you connect them in series, they will all give you the same level of brightness because the same amount of current flows through them. So for series connection, the same level of brightness is obtained. So if you have 100 bulbs connected in series, their brightness level will be the same because of the fact that the same amount of current flows through them. In fact, for this, the advantages are not many. The disadvantages actually outnumber the advantages. One of the disadvantages is that loads or appliances that uses different magnitude of current can never be connected in parallel. Example, you can connect a bulb, iron, heater, fridge in series because these are appliances that would require different current for them to work. So when you connect them, these appliances in series, some will be able to work, some will not, because they require different current to operate. But connecting them in series, you are giving them the same current. So some will be able to work depending on the magnitude of current they require. Others will not, because iron heater will require greater or a larger magnitude or value of current. So when you give them the same, it will not be able to operate them. Please, are you okay?
Please, can you say the point again?
Gadgets or loads that require different current to operate, okay, cannot be connected in series because the idea is that they require different amounts of current to work with, to start. But here is the case, by connecting them in series, you are giving them the same current. Insira, Misedia requires 5 balls of kenke to be satisfied. Insira requires 2. Rachel requires 10. Mary.
Hey, Mr. J.
Yes. Mary requires 15. As for K, maybe K requires 25. To be satisfied. Here is a case at the school dining hall. We are giving 2 balls of small kinky. What do you think will happen? Mr. Celia will be annoyed. Rachel will be more more annoying. After okay, he will start fighting. Okay, so that is a practical thing. We need different current to work, and you are giving us more the same. It won't work for some gadgets. The reason for which devices that require different amount of current can never be connected in series. Please, I hope it's clear.
Yes, sir.
Okay. The other disadvantage is that look at series connection. The moment there's a problem, fault in one, maybe there's a break in this wire conductor, all these will not be able to work. Only this one would work. But if there's a break in this one, the rest will not be able to work. That's the problem. Okay, so when there is a fault in one of the resistors, the rest will not be able to function because of the nature of the connection. So now look at advantages of parallel connection. In parallel connection, different current flows through them. So I think you can all be able to apply that. Oh, okay, then when there is a need of you to use devices that require different currents, it's a must that they are connected in parallel, because they will get that. You'll be able to provide them with the magnitude of current they will need. Now, the other advantage is that with parallel connection, when there is a problem in one of them, the rest will be able to work. So when there is a fault here, they'll all be disconnected if there is a fault from the source. But if there is a fault from one of them, only that resistor or load is disconnected. The rest will be able to work.
So what was the first?
Pardon?
What was the first point again?
I'm talking of the advantages of parallel connection. Different loads or loads that require different currents, ideally must be connected in parallel, because in parallel connection, different currents flows through the resistors. So if you are connecting maybe heater, fridge, iron, washing machine, air conditioning, then the connection must be in parallel, because these are gadgets that require different current for their operation. And so by connecting them in parallel, you can be able to give them their individual current requirement for them to work with. Larry, are you there? Mary
Yes,
Clark,
please.
respond or else I'll crack you. Then the other advantage is that when there is a problem, fault with any of the resistors, the other resistors can be able to work. Okay, so these are advantages. So in our homes, sockets in our homes are connected in parallel, so that when there is a fault problem with one, others can work. So the sockets in our halls are connected in ring system. Ring system is in parallel connection. The only disadvantage with the parallel connection is that devices that require different voltage drops or potential difference cannot be connected in parallel, because by connecting them in parallel, you are giving them the same voltage. But when you are using devices that will require different voltage drop, then the parallel connection will not help in this regard. Please, are we okay?
Yes, sir.
All right. I think this is where we'll end. In our next meeting, I'll bring a question so we can apply all that we've learned. Is that okay? So
Yes, sir.
take care of yourselves and revise. Mary, go and watch the video I posted yesterday before so that you can pick up from where we began. Is that okay?
Yes, please.
Okay. Rachel, Kay, Mary, and Inshira. Bye-bye.
Bye.
Bye.